Hi friends, we are talking about this problem of finding largest area under a histogram, right? So what is a histogram? It is a bar graph like this, and we want to find out what is the largest area that I can get inside this histogram by making a rectangle, right? So you might make a rectangle like this and you will get some area, and it is given width of each bar is 1 unit, right? So let us do the indexing from 0. So what is the area you can get? You will have a height of 2 and you will have a width of for this box as 5. This is 10 units. Or it is quite possible that instead of drawing this rectangle, you are drawing some other rectangle, maybe like this. The only constraint is that this rectangle should lie completely inside the histogram. So what is this area now? So the width is 3 units. And what is the height? The height is 4 units. This is the 12 units. So you can clearly see this area is bigger. So we won't take this as our answer. Instead, we will take this as our answer. So there are many rectangles possible. Out of all possible rectangles, we have to figure out the area corresponding to the maximum rectangle in this bar graph. So there are a lot of approaches to solve this problem. This is a very classical problem. So the first approach is the brute force method, in which you will pick all starting and ending points, right? So you will pick that I'm starting from this point and I am ending till this point. You will know the width using j minus I formula, and you will also know what is the minimum height bar in this region, right? So brute force will take you O of n square steps, where n is the number of bars. In the second approach, it is a divide and conquer approach which can be used, and divide and conquer method I'm not going to discuss in this video, but this method is capable of solving this problem in n log n time, right? The third solution which I'm going to discuss is a stack based solution which can solve this problem in O of n. We will try to understand how this solution works and what is the intuition behind this algorithm, right? So we are going to discuss a stack based solution which works in O of n time. So let us start with this solution, right? So what is the idea? So let us first try to understand the idea behind the stack based solution. So clearly we will maintain one stack, and what we will do, we will push the current bar into the stack if it is higher in height than the stack top, higher in value than stack top, right? Otherwise, what we are going to do, otherwise we are going to pop all the bars of greater height. Suppose if the current bar is smaller, then we are going to pop all the bars which are inside the stack and are of greater height, right? And in this solution, when we are going to do the popping, right? So what is going to happen, that for every bar, for let's say every bar x, what I'm going to do is this will be pushed into the stack once, push into stack once, and we are also going to pop it once, right? Second is we are also going to pop it once. So since every bar is being pushed only once and it is being popped only once, we are going to say the solution is having O of n complexity, because every bar is getting into the stack once and getting out of the stack once, right? And when we are going to do the popping, we are going to find out area of the region considering the current bar has the minimum height. This is a very important concept. Current bar as the minimum height bar. This is what we are going to see. I will give you one example. So suppose you have a bar like this, and suppose you are going to let us say we are going to pop up this bar, right? So what I'm going to do, I'm going to find out the area of the region considering this bar has the minimum height. So what I need to do, I need to know what is the rightmost bar which is smaller than it, and I also need to know the leftmost bar which is smaller than it. So let's say this is the rightmost index, this is the, let's say, leftmost index. Let's say numbering is 0 1 2 3 and 4, right? And I want to figure out what is the width of the region. So width of the region, this is the width, right? So width is nothing but r minus l minus 1. So this is the width of the region into height of the minimum bar. So minimum or the current bar, because we are saying that the bar which we are going to pop is the bar with the minimum height. So for example, let's say the height of this bar is 3. So the area is going to be nothing but 4 minus 1 minus 0, right? Into 3 units. So this is going to be 9 units, which is perfectly fine, right? This, I'm going to use this kind of logic for this problem. So let us see here, right? Now let us see here. So our area is going to have two formulas, right? So we are going to compute the area, and this area will have two formulas. We will see the intuition behind it, right? So the one formula is, if the stack is not empty, if the stack is not empty, then the area is going to be height of the minimum bar into rightmost bar which is less than height minus leftmost bar which is less in height minus 1. So this is one formula. The second formula is going to be height of the minimum bar if the stack is empty, right? Height of the minimum bar into the rightmost index if the stack is empty. Suppose you have something like this. You have or maybe you have something like this, only you have only one bar left, right? And suppose this is the minimum bar, and this is the minimum bar, and you know the area, and you have suppose only this bar in the stack, then the area is going to be the entire area, right? This is going to be the entire area, right? So when you will have such a case, you will find out that this is the only bar left into the stack. In that case, after popping out this bar, you will find the stack is empty, and in that case the area is going to be the I, which is the current last index, the rightmost index, into height of this bar. Let's say this height is x, so it is going to be x into I, right? This we will see, don't worry. So we will come to this bar, we will, right, come to this case as well. But before that, let us try to understand this entire scenario with the help of one example. So let me draw this one again. Let us draw the bar graph again. So this height is 6 units. Then I have a 2 unit bar. Then I have a bar of 5 units. Then I have a bar of 4 units. Then again I have a bar of 5 units. Then I have a bar of again 1 unit, and then I have a bar of again 6 units. And this is the bar graph I have. And let me do the numbering indexing also. 0 1 2 3 4 5 6 and 7, right? So the elements in the array are given as the input. This bar graph is given as the elements of the array as input. So elements are nothing but 6 2 5 4 5 1 and 6. This is the input array, and our algorithm will now process what is the largest possible area. So as I told, the area is going to have two formulas. We will see what these formulas are, and we will try to use these formulas as well. So if the stack is empty, then you are going to have a formula like this. If stack is empty, then your formula is going to be, area is going to be array of stack top, the topmost element you have, into I. I is the current index. We will see. Otherwise, if the stack is not empty, the area is going to have a formula like this. Array of top, which means the current node which we are popping, into the current index. I is the rightmost index, minus s dot top. S dot top minus 1, right? So this is the previous top. It will form the leftmost index, and minus 1 because we are finding out the width of the region. So it is the rightmost smaller element, and this is the leftmost smaller element. And I know if the current element is higher or the stack is empty, I'm going to push it. Otherwise, I'm going to pop some of the elements, right? Now let us dry run each and every step. So in the first step, I know my stack is going to be empty. So I have a stack which is initially empty. So what I do, instead of pushing the value of the 0th element, I will push the 0th index. So I push the index as 0. So this is my stack. If the stack is empty, then I'm going to push the first element. Now let us come to the second step. In the second step, I can see the current element is having a lower value than the stack top, right? So the current element is 2 and stack top is going to be 6. So 2 is lesser than 6. So what I'm going to do, I'm going to pop off, right? So we are going to remove this bar. How? So I'm just going to make the stack empty by removing it. So if I remove it, the stack will become empty, and we will find out what the area is. Area is going to be nothing but area due to this, area due to the bar which we have removed. So area is going to be nothing but 6 into something. Now I remember we have used two formulas, right? So area of top, what was the topmost element? 0. So area of 0 is nothing but 6 into I. What is I here? I is nothing but 1. So 6 units. This is the area that this bar was contributing if it was being considered. So we have removed this bar, so this has been removed. Now it's time to talk about, and now we can push this one into the stack. So let us push this one. Why? Because the next rightmost bar was 2 and there was no leftmost bar. So the area due to this bar is going to be 6 units. Let's talk about the third step. Let's talk about the third step. In the third step, you can see that we are at this index, we are talking about this bar. So since it is greater in height than the previous bar, we can directly push it. So we can push it onto the stack. So after 1, I can push the index 2 because array of 2 is higher. Let's talk about the fourth step. Now again, you can see that this bar is smaller than the previous bar. So it means that this bar is an obstacle to the previous bar. Right? So now we should remove the previous bar. So if the current bar is smaller, then we should remove all such bars which are inside stack and are having a higher value. So for the current bar 4, I know only this bar is having a higher value. So I am going to remove it. So I'm going to make it orange and I'm going to count the contribution due to this bar. If this bar is being considered as the smallest bar. So we are going to compute the area now. So area is going to be, so in the fourth step, I'm going to pop the second bar. This is being getting popped now, and we are going to compute the area. What is area? So area is nothing but 5 into something into what? So 5 into the rightmost bound. Rightmost bound is the current element. So it is the current element index I 3 minus the leftmost bound. Leftmost bound is the topmost element in the stack. So leftmost element is nothing but index 1. This is the leftmost element. So this is nothing but the topmost element into the stack. So minus 1 and minus 1. So it becomes nothing but 5 into 1. So which is again 5 units. So you can clearly see the loss of area or the maximum area that this bar could form alone was nothing but 5 units. So we have removed this bar as well. We have removed this bar as well. In the fifth step, again I am standing at this position. I am considering that the current bar is having a height of 4 and the previous bar in the stack is having a height of 2. So I can directly push it. So in the fifth step, after 1, I push now the third bar. So I push index 3 in the stack. Let us now consider the sixth step. Right? So I'm going to remove these steps. So let us see what happens in the sixth step. So in the sixth step, what I'm going to consider, I'm standing at this position and I know I am able to see that this bar is clearly having a higher value than the previous bar. So in the previous bar in the stack was bar having index 3 which is having a height of 4. In the sixth step, I can clearly push fourth index over the third index. So I'm pushing it. Let me talk about the seventh step. Now this is an important step, right? So we come to the index 5. We see that this bar is now having a lower value than the previous bar. It means it is an obstacle to the previous bar, right? So what we are going to do, we are going to remove the previous bar. So this is the bar we are now talking about. This now needs to be removed because the next bar is having a lower value, right? So we are not going to consider this bar again because it is going to be removed. So we remove it from the stack and our stack now becomes something like this. So 1 3 And what is the area we are going to get? So area what we are going to get is, now let me write about the area, is consider the current bar as the minimum height bar. So taking this bar as the minimum height bar, so it is going to be area of top, because this was the topmost bar here, right? So area is going to be 5 into rightmost obstruction is at index 5. What is the leftmost element here? इसका जो leftmost element है, that is the third index. So minus 3 minus 1. So it is going to be 5 units, right? So you can clearly see the orange region has an area of only 5 units. And I have used again this formula for computing the area, right? And again, this bar has been removed. We are at this index. Now we will compare one with the previous index. So what is the previous index? 3, right? Again, one is having a lesser value than the previous index. I can say one is an obstruction to the third index, right? So one is an obstruction to the third index. We are going to remove it as well. So this was one of the area we had computed, and now we are going to compute another area, right? So what is the new area now? So let us write the areas we have computed so far. So 6 units is one area, 5 units is one area, 5 units is another area, right? Now let us compute the area again, because this bar is providing hindrance to this block, right? So what I'm going to do, I'm going to remove it. We are going to remove this bar now. So this bar is now getting removed, and we know the rightmost occurrence, the rightmost smallest element is at 5th index, right? So considering that this is the minimum height bar, right? What is the maximum area I can form due to this is height of this bar, which is 4 units, into the hindrance at the rightmost unit, which is at the index 5, minus the hindrance at the leftmost unit, which is at the index 1, which we can know from this place, because after removing this, the new top is now 1, right? This was the old top, the new top is at 1 minus 1, right? So this is going to be 4 into 3, and this is going to be 12 units, right? So this is going to be 12 units now. So you can clearly see what is the rectangle we are making at this place. So we are making a rectangle like this. This is the rectangle which is of the area 12 units, because the rightmost occurrence occurs at this position, and the leftmost occurrence hindrance, or the leftmost smallest element, occurs at this position, right? So that's why we are able to find out this area now, and from the stack we are going to pop this out, right? So 3 is now popped out. In the 8th step, in the next iteration, what we are going to do, we have only one node inside the stack. We have only one node inside the stack, and again this is having a area of, this is having a height of 2, and the current node is having a height of 1, right? So current bar is having a height of 1 again. So this is an obstruction to this, so this is obstructing the area, and for this let us try to find out the answer. So now in the 8th step I have only one node, and if I pop it out, I will came to know that the stack is empty, right? So what is the area we are going to form is, so it is going to the height of the minimum bar. This is the bar we are talking about, and the height of this bar is nothing but 2 into, now since after popping it the stack is empty, so into I. So what is I here? I is nothing but the 5. So 2 into 5, it is 10 units, right? So the area that this bar was able to form as the minimum height bar was 10 units. Let us see what is this area. So this area is this area basically. So this area is 10 units. So this was the area which was formed due to this bar being the minimum height bar. This area is 10 units. So I have used this formula to find out the area. So area, one of the areas is 10 units. And my stack is now empty. And since now we can, since the stack is empty, we can push the current bar. So current bar is having a height of 1 and it is having an index of 5. In the 9th step, I push it, right? And in the next step, I come to this position and I see that the current bar is having a higher height. So after 5, I push the index 6. The 6th index is now pushed into the stack. So in the next part, I go here. The array is now complete, right? So when we come to this position and we have finished with all the elements, we will just pop out elements and we will find out the answer, right? So for this position, again I'm going to compute the area. I'm going to pop this element 6 and I'm going to say with 6 as the maximum height, minimum height bar. So the maximum area I can make is nothing but 6 into the rightmost index. The rightmost index is nothing but 7 minus the leftmost index, which is lying here, is 5 minus 1. So the maximum area is going to be 6 units, right? So it means that we have popped up this bar also, right? So considering this bar, the area we can make is 6 units, which we have written here. The only bar now left is this bar. The only bar left is now this bar, right? So in the stack I have only one bar, right? And if I pop it off, so considering the height of this bar, which is nothing but array of 5, which is 1, sorry, yeah, so it is 1 unit into, if the stack is empty, I use this formula, into I. So into I is nothing but, I is here 7, right? So since this was the minimum height bar and this was the only bar present, so I can consider the entire array in its area, right? So to find out the area, I can use this entire array and I know the width of this array is nothing but the 7, which is same as the value of I. So 1 into 7 is 7 units. So the area we can make is 7 units, right? So you can see out of all these areas, the area which is maximum is 12 units. So these are the values of areas. So you can make one variable maximum area so far and you can update that variable to find out the maximum area, right? So this is the maximum area that we could make, right? So you can see you got 7 values of areas and each value represents area due to a bar, right? So each area is due to considering each bar as the minimum height bar. So the complexity of this method is O of n, and we have popped every bar just once, and when we are popping, we are finding out the area due to every bar. In the next part, I will show you the code. I hope you enjoyed learning from this tutorial. So hit the like button and do not forget to subscribe our channel Coding Blocks India on YouTube. For more such tutorials, visit our website codingblocks.on.